Hi, everyone. So today we're talking about impulse. So starting with this force equals dp divided by dt, something we've talked about before. Integrate and isolate momentum to find a useful equation for impulse. So how we get F equals dp dt, I'll show you that real quick. That starts with F equals ma. A is just the derivative of velocity with respect to time. Then you get F equals the derivative with respect to time of mv, which is the derivative of momentum over time, because mv can be momentum, right? So that's how we start there. So we've done that. Now we are looking for an equation for impulse. So if we start with F equals dp over dt, so we can actually multiply the dt to the other side, so you get F dt equals dp. Okay? And then if we integrate these two, the integral of force over time is actually an impulse. And if we integrate dp, that just means change in momentum, right? So this can tell us that if change in momentum is p final minus p naught, that impulse is really just change in momentum, right? And we'll actually talk about that a little bit on this next question when we talk about its unit as well. But impulse is really just any change in momentum, right? We talked about how in the other video, impulse is a change to an object or a system's momentum. Now, what is the direction of impulse, and what is its unit? Well, since impulse can be described as the integral of force over time, right? You're exerting a force on an object over time to change its momentum. The impulse vector will be in the same direction as the force vector. Wherever the force is being exerted, that is the direction of impulse. And it then asks, what is its unit? Well, we've seen the integral of force before, right? Work is the integral of force over some distance, right? So, and work's unit is a Newton meter, right? Newtons times meters. So here, impulse is just going to be a Newton second. And if you look at what a Newton second is, if you take a Newton, which is a kilogram times meter over second squared, multiply that by a second, then you get a kilogram meter per second. And this is also the unit for momentum. So if it's the same unit as momentum, you're really just taking one momentum, take one momentum, subtract another momentum, you're just going to get an amount of momentum, which also goes to show that the unit for both is the exact same. They have the same unit because they're really describing very similar stuff. Impulse is just describing how much impulse was, impulse is saying how much momentum was either given or taken away from an object or from a system. So that's the direction of impulse and its unit. Number 3 says, a martial artist moves his head backward when hit in the face. Why does he do this? So if we look at the relationship between impulse, right? Okay, say we have a constant impulse, right? And we have two scenarios. One, F delta t, where you get hit in the face with a certain force and the collision lasts a certain amount of time, delta t. Well, if you move your head backwards as you get hit, that actually extends the amount of time the fist is in contact with your face, right? But the impulse, we are saying, is constant. You can't change we're not going to change the impulse. So if you increase your delta t, you would then decrease the force that is felt, right? And if you want to increase the force that is felt, decrease the amount of time that you're in contact with the fist, right? So instead of waiting for the fist to come to you, you can just headbutt the fist. You're going to increase the force that's felt, right? This also has to do with a discussion over relative velocity. So, for example, say that you are going 60 miles per hour and you hit a barrier. Your speed goes from 60 to 0, right? Your delta V is technically just negative 60, and your acceleration is going to feel like that. However, when we talk about relative velocities, say you're going 30 miles per hour and you get in a head-on collision with someone who's also going 30 miles per hour. If you both come to a stop, your delta V is really negative 30, but relative velocity is actually going to change that, right? So it's going to feel like you accelerated not just 30, but 30 plus 30. Okay? It's going to feel like you accelerated from 60 to 0. So that relative velocity, that relativity actually confuddles the math there a little bit. Then if we say something similar, say you're going 30 miles per hour and someone hits you going 20 miles per hour and you get rear-ended. Well, then this also, we don't really have a delta V. We don't know the result of this collision, but that acceleration that you feel would really be as if you changed your delta V at negative 10 miles per hour, right? The relativity there is important in analyzing the real life circumstances. Sometimes we don't always talk about that kind of stuff, so I wanted to bring that in, that the velocity of both objects is really important. So when we talk about this impulse, right, if you extend the time that you're in contact, you can actually decrease the force, assuming that the impulse is a constant that can't be changed. All right, now let's talk about finding impulse graphically. Okay, what is the graphical definition of impulse? So the graphical definition of impulse is the area under this F versus T, right? We have F versus T right here, and this shaded in area, that is impulse, right? Or you could say that that would be the integral of F dt, right? Talked about that before. That is also the delta P, the change in impulse, or I'm sorry, the change in momentum during that time frame. So we've talked about that quite a bit. That is the graphical definition of impulse. We talked about that this video and the previous video. Now, what is a time averaged force? So this is, say, for example, you don't know the force, but you know the impulse. So if you want the time average force, I'll call that F bar, you can take the impulse and divide it by the delta T, divide it by how long that force was applied, and you can find what was the average force felt during that time. So two very different ways to find impulse. And we'll go over a couple examples here. So first we have F versus T curve hitting a baseball. We hit a baseball at the 1 millisecond mark, and well, I guess the contact is from the 1 millisecond mark to the 2.5 millisecond mark while we hit a baseball. It peaks at 18,000 newtons. We want to determine the impulse that's delivered and the average force exerted on the ball. So let's find the impulse. We can find the impulse simply by doing F times delta T. The force, actually, you know what? We don't want to do that because that's not going to give us the right answer. What we want is we want the area under that curve, F dt. Well, the area under that curve is going to be a triangle, right? So the impulse, and my cursive eyes are erratic. So we have area of a triangle, 1/2. The base is 1.5 milliseconds or 0.0015 seconds. And then your force or the height of the triangle is 18,000 newtons. And when you put that in your calculator, that will come out to 13.5 Newton seconds. That is the impulse on this baseball. A lot of force in a very small amount of time. Now, what if we want the average force? Well, if we want the average force, I'm sorry, that's the wrong symbol. Time average force, you want to take the impulse divided by the change in time while that force was being applied. So this average force would be 13.5 Newton seconds divided by 0.0015 seconds. You can see those seconds will cancel to give us newtons. And this will be 9,000 newtons on average over that 1.5 milliseconds. So you can see that that is significantly lower than the true maximum peak of the impulse, right? This is what we're really looking at when we look at average, saying that this is approximately how long that force or the felt force over that period of time. Then what would happen if a baseball became springier? So this was actually something that happened in Major League Baseball. They started calling them juiced balls as the new steroids, where the baseball, they called it juiced because it was actually springier. I think they changed the manufacturing of the baseball. And since it was springier, it had more time to be an impact, right? So if we say impulse is F delta T, well, here we can't say that the impulse is constant, but we can say that the batter is going to hit the ball with the same amount of force no matter what. However, if you increase the time of the contact by making it a springier baseball, meaning it'll compress on the bat and spring off for a longer period of time, you can actually increase the impulse because your force will be constant. So that was allowing for more home runs. It was actually a little controversial at the time. Okay, next, a couple of different ways to find impulse. We have a car crash. Okay, we're traveling at negative 15 meters per second initially. Then after the collision, we're traveling at a positive 2.6. This is a crash test of an automobile. Automobile has a mass of 1.5 times 10 to the third kilograms. Collides with a wall with the velocities as shown, and the collision lasts for 0.15 seconds. We want to calculate the impulse and the average impulsive force. So if we want impulse, okay, what we know, I'll put my givens first. That makes more sense. Mass is 1.5 times 10 to the third kilograms. Delta T is 0.15 seconds. Delta V, let's see, that is V final minus V naught. So we have 2.6 minus negative 15 to give us 17.6 meters per second as our delta V. Yeah, that's everything we have there. So we want impulse. We don't have force. So to find impulse, we will use delta P, which is P final minus P naught, which would be mass times delta V. So we would take 1.5 times 10 to the third kilograms times 17.6 meters per second. And that will give us 26,400. Zoom in. We got 26,400 Newton seconds of impulse, or kilogram meters per second. You can also call this 26.4 kilo Newton seconds. So that's our impulse, right? Next, it asks for average impulsive force. So if we want the average impulsive force, we want to take that impulse and divide it by delta T to see what is the average force this person is is feeling while they are in this collision. So we would take 26,400 Newton seconds divided by 0.15 seconds. That'll get rid of those seconds there to give us newtons. So then if you put that in your calculator, you should get about 176,000 newtons, or 176 kilonewtons. That doesn't sound like it feels good. With that average force, even 100, I mean, it's 150 milliseconds, so you wouldn't think that it lasts a long time, but that's a lot of force. I don't want to feel that for any amount of time. Now, what do airbags do to change the crash for a passenger? So we said that this is a high force, right? So what an airbag does, right? When we're looking at impulse, right, as delta P, in a car crash, you can't change delta P, right? You can't change the mass of the car, obviously, and we also can't change the delta V. You're going to crash. It happens. How do you make it safer? Well, what you can do is you can look at how we can not change this constant impulse, but maybe change the force, right? So we talked about if you increase your delta T, you can decrease the force, right? Because like we said, impulse, it's going to happen. You've got mass, you've got delta V, it's going to happen. But you can decrease the force felt by increasing the contact time. So actually making the crash last longer will decrease the force delivered to the driver, and that is being delivered to the driver usually by the steering wheel, right? Steering wheel and the seatbelt. But as that airbag comes out, that actually allows you to gradually slow down as you go into the airbag. Whereas if you just go down onto the solid steering wheel, that's just going to cause a sudden stop, right? So the seatbelt slows you down, the airbag slows you down over a much longer period of time, which then decreases the force felt, as we can see this little guy right there. All right, so that is our video on impulse. Next, we will be continuing on and we will talk about different types of collisions.